We started off with that x. So we took the last number and put it on top, and the middle number put it on bottom. If there was a number in front of the x, that's when we had to, or in front of the x squared, that's when we had to do that longer split the middle method and multiply the 2 on top. But for this, if there wasn't a number in front of the x squared, we could do the shorter method. So what do we have to do from here now? 2 numbers that multiply to get your numerator, or the top part of your x, and add them together to get your bottom. So 3 and 5, multiply to get 15, add to get 8. And then what was our final step from here? X plus 3, x plus 5. That's our 2 factors. Once again, we had the longer split the middle method if there was a number in front of the x squared, but there wasn't a number in front of the x squared. All we had to do was that quick find your 2 factors and then jump right to your solution. So once again, we'll talk about why this is important to know tomorrow and how this affects with quadratics and what the key features relate to. But we'll worry about that tomorrow. But we can't forget factoring. That is an important piece. So last unit, when we were talking about different types of polynomials, we talked about what is the standard form of a polynomial. So the standard form of a polynomial, depending on what type of polynomial, it was always from highest degree to lowest degree, or highest power to lowest power. So if you had a polynomial that was like 4x to the third minus 2x squared plus 1x plus 3, this would be a standard form polynomial because you're going from highest power to lowest power. So because this week we're talking specifically about quadratics, quadratics are always x squared, x, and then some other number. Or really, the definition of a quadratic, in order for something to be a quadratic, it has to have an x squared. If it doesn't have an x squared, it's not a quadratic. So our standard form of a quadratic, our sort of generic basic, if you were to write a quadratic without really having any information about it, would be ax squared plus bx plus c. That a, b, and c, those are just numbers. So whatever number is in front of your x, whatever number is in front of your x squared, whatever number is at the end. So a, g, b, and c just represent numbers. So this could be 3x squared plus 2x plus 1. That's a quadratic in standard form. Are we okay with this so far? So anytime a quadratic is in standard form, you just want to write it from highest power to lowest power. Our generic form of a quadratic is this. If I sort of like how our line, if you have a generic equation for a line, it's y equals mx plus b. A generic form for a quadratic is ax squared plus bx plus c. Once again, a, b, and c are just numbers that are determined, or whatever your number doctor is like. So whatever that number is in front of the x squared, that's a. Whatever the number in front of the x is b. Whatever the number at the end, that's c. Are we okay with this so far? Okay. So of these equations here, which of these are quadratics and which of them are not quadratics?
Those ones. The third one from the left.
The third one from the left is or is not a quadratic? Is not a quadratic. Why?
Because it doesn't have x squared.
Good. It doesn't have x squared. Are the rest quadratics?
Yeah.
Yes, because they all have x squared. That is the only basic piece you need to be a quadratic. The rest, if you think about it, this one, what's the number in front of the x squared? If there isn't a number. So if there's not a number in front of the x squared, your c is going to be 8, or negative 8. What would be that number in front of the x? Because we don't have an x. If I have no x's, I have a 0x. So even if we don't have all the terms, even if they are not all written out, we can still know what those values are. You can still know there's a 0 in front of that. There's a 0 for your b because it doesn't show the b. Or if it didn't have, let's see, I don't have an example. So this one over here, it doesn't have that plus c at the end. So because there's no number at the plus c, your c would be 0 because it doesn't show a number. Are we okay with that? So even if the numbers aren't there, you can still determine what they are, whether they're visible or not. You okay, Brad? But once again, it needs x squared. If it doesn't have an x squared, it's not a quadratic. This would be a linear function without a quadratic. Remember, in order for something to be linear, it just has that y equals mx plus b. Actually, do you have a question? Oh, okay, sorry. Dylan, yeah.
So the first one.
So all three of these are quadratics because they have that x squared in them. It's okay for a quadratic to be missing some pieces. So this one's missing the b, x. This one's missing the c. That's okay as long as it has that x squared. All right. Stand up. Actually, let's see. Dominic and Wyatt, can you go grab me 2 graphing calculator cards or 2 graphing calculator trays from them? I forgot to grab these. So sorry. Or as many as you can grab.
All the calculators.
We're going to be talking about graphing quadratics and what sort of they look like when we graph them, and what are some special features when we graph them. But rather than having to graph them by hand and finding what this point is and finding what that point is and all that stuff, we're going to graph them onto. I'm going to have you graph them on the calculator so you can sort of see what they look like, and then I'll draw a picture on here so we can. Thank you, boys.
Good job, Wyatt.
Good job.
I can't.
Just come up. That'll make it much quicker.
Oh my gosh.
Oh my god. I got you, Jim.
Oh yeah, I want to look at that.
We need these graphs.
Did you actually say that? Yeah.
Does everyone have a calculator? All right. Once again, just sort of a review on how to graph these calculators. Grab your calculator. Turn it on, of course.
Whoa.
Go to the y equals in the top left corner. There's a button that says y equals. There. And it should say y1, y2, y3, so on and so forth. So y equals in the top left. From there, we're going to graph this function. We're going to type in x squared. So x is right next to the green alpha button. And then squared is down below the green alpha button, a little, like 4 buttons below.
Wait, why don't we?
So x is next to the green alpha button, and then x squared. So the x button looks like x, t, it has a little circle with a line through it, and then x. Just hit it once and it should be an x. So the very first line should say y1 equals x squared.
Wait, where are we?
Oh my god.
Hit y equals on your button. Hit x, which is right next to the green alpha button. And then hit x squared, or the square button, which is down below. All right, so you should have y equals x squared on your calculator. If you look over in the top right corner, it should say graph. Hit graph, and it will graph your function for you. Wow.
Cool.
It does word.
I made it up.
Cool, man.
Me too.
All right. Wow. So we should have a graph that looks something like this on your calculator, correct?
Yeah.
Not so skinny.
All right.
Mine's cooler.
If your graph looks different, go to that middle button,
Right.
hit zoom, and then go and hit 6. So zoom 6. That will fix. It will regraph your function, but it will regraph it with a 10 by 10 scale.
It just made it bigger.
Zoom 6.
Zoom does, bud.
Did you hit zoom 6? Right, yeah. All right. Whoa. So we have this function. What are some things you notice about this graph? Why? What are some things you notice? All right, guys, talking too loud right now. What did you say? So the domain on each side is going on towards infinity. It's going up and up and up, and up and up and up on both sides. Good. What else do you notice? What was that? It only hits 2 boxes. Oh, it's only in 2 quadrants. All right. Anything else? What else do you notice?
Looks like what the last one.
So it's that U-shaped.
Yep.
Specifically, if I were to cut my quadratic directly down the middle,
It'd be symmetrical.
it's symmetrical. So every quadratic will always be symmetrical directly down the middle. We call this middle point down here, at the very bottom, we call that the vertex. So that bottom point of a quadratic is always going to be called the vertex. Let's stop that, please. Right. Do you notice anything else?
It goes out of the graph. Oh, it never hits each other. It never touches.
Okay. They're always going to be going outward, away from each other. All right. So we're going to graph another one.
Oh. Exactly.
All right. So once again, go back to y equals on your calculator.
What?
And now we're going to change this.
Oh, I broke it.
Rather than just being y equal or x equals or x squared, I'm sorry, we're going to change it to x squared plus x. So we're going to hit your plus, then hit your x sign again, and then minus 6. So x squared plus x minus 6.
Whoa. Whoa. That's what makes it bigger.
Offset.
Same danger.
No abomination. Just put it down. Keep it put it down.
Right. Right.
It's the same thing. Yes, it is. I just did it. Oh, it moved over.
It's not centered now, Jarvis.
Yes, it is. I'm sorry. It's not safe.
Right.
Oh, wow, it's way bigger. This is gonna bother me.
We'll do it.
No, you want it? Yeah.
AJ, watch your language. Watch your language.
Yeah, AJ.
Yeah.
All right, we should
Oh,
have a quadratic.
A little bit more off-center.
Yeah.
Mine is way off.
My graph's probably not perfect. Yours, it should be probably a little bit more pushed to the left side.
I can't look at this.
What are some things you notice about this one?
Oh, yes. It's hard. It is also going, it's not symmetrical.
It's going up, like the last one. Once again, it keeps going up and up and up in both directions, and keeps going out and out. It's not centered this time. Notice anything else? It's in all four quadrants this time, so it went both. Our first one was just above the x-axis. This one's now below the x-axis and went down. Anything else? It's still symmetrical. It's not symmetrical about that x-axis or the y-axis anymore, though. It's now symmetrical more on a line that's like right about here. Once again, that symmetrical line should pass right through that bottom point of your quadratic. So because it's a little off-center, that line is going to be a little off-center as well. Anything else? All right, we're going to look at one last one on your calculator. So this is negative x squared plus 9. So make sure to get that negative in front of the x squared.
Plus 9.
Plus 9. Negative x squared plus 9. So go back to y equals, don't take it away.
What is it? Oh.
Whoa, it's an upside down mountain. It's right side up mountain.
It's an upside down mountain. Wow.
It was an upside down mountain, and the mountain was upside down.
Oh, a hole, Dylan? A hole?
I did it again. That's a nice straight mountain.
All right, what is different about this one? It's upside down.
It's an upside down mountain. Upside down.
Well, what was different about this graph or the function in this one compared to the other? We had that negative x squared. If that number in front of the x squared is negative, your quadratic will open up downwards. If it's a positive, it's going to open up upwards. Do you notice anything else?
It's not offset.
It's not offset.
Center.
What's different about this one compared to the other one that was offset?
It's off. The 9 is off. The 6 would be even.
Okay.
What?
What is that?
Anything else that was different about this function or this equation compared to the last equation? There's a negative sign. The negative sign is going to make it open downward. Not quite. So the last one was x squared plus x, no, plus
x minus 6. Yeah,
plus x minus 6. So that was our last one. What's different about these two?
There's another 1x.
This one had
2x.
that bx in it. So whenever that has that middle term, if there isn't a middle term in your quadratic, it's going to be perfectly centered. If there is a middle term in your quadratic, it's going to be off-center. It's going to lean to one of the two sides.
Oh.
Yes, that's right.
So if you put a number in front of the x, then it would swing to like, and be swinging that way more. What?
If it's a positive number, it should swing to the left. If it's a negative number, it should swing to the right. Should typically. Do you notice anything else about this one specifically?
Well, no, you don't.
What's the highest point of this quadratic?
9. Oh, that number's at the highest point. That's good.
Well, where's the lowest point of this quadratic? Was this one on -6 though?
Look closely.
It was really close, but it was a little off. Where's -6? What's happening at -6? This is a bad example. I'm sorry. This one's hard to see. We'll see it in just a moment. But 9. Okay. Anything else you notice at all about this quadratic? Any other things you're picking up? All right. So we'll continue to learn about different features of the quadratic as we continue throughout this unit. So these are just some of the things we want to pick up today. But there's 3 main types of features from a quadratic. There's 3 main things you're typically looking for. So when you're solving problems and then you're solving with a quadratic, there's typically one of these 3 things is what you're looking for. When we start looking at real-world examples, real-world modeling problems, we're going to be looking for typically one of these 3 things. What might be some situations where you have a quadratic in real life? What are some real-life examples of quadratics?
Roads.
Roads, how are roads quadratic?
Then they're not complete. Yeah, U-turn.
U-turn, okay. So you're like going around a curve or turning around your car, okay. That can be a quadratic. Anything else?
When you're throwing things up and then they go back down.
When you're throwing things up, or like shooting a basketball or throwing the football, it's like a negative quadratic. It has that quadratic shape. Good. Power lines, if you look, you're driving down the road, you see a power line. They swoop like a quadratic. I could come up with a lot more examples, but we'll leave it at that for now. So we're going to look at a lot of different examples, especially projectile motion is the biggest thing that involves quadratics. Throwing things or anything moving through the air is a big piece that involves quadratics. And we'll talk about a lot of different things we look for. But we have 3 major features that we're looking for. Number 1 is the y-intercept. So where does that quadratic hit the y-axis? And so there's 2 ways of finding this. One, just looking at the graph, just graphing it on your calculator or graphing it by hand and looking, oh, I touch my y-axis right there. So 0, 2, or 0, -2 would be my y-intercept. Another way of checking, the coordinates for your y-intercept. Because it's a y-intercept, 0 always has to be for your x. X can't be anything but 0 for a y-intercept. In C, that last number of your quadratic will always be the y of your y-intercept. So in this case, -2 is where we cross the y-axis. So -2 would be the last number on that quadratic. 9 was where we crossed the y-axis on the last problem. So 9 was the last term of that quadratic. -6 was where we crossed the quadratic on the second problem. So -6 was the y-intercept. So that last number will always be the y-intercept. So that's an easy way to determine what the y-intercept of quadratic is. As long as you have the function, you know what it is. X-intercepts. If you look at the quadratic and look where it crosses the x-axis, these are important points. If you're throwing a football and you want to see how far does the football go until it hits the ground, you're looking for an x-axis or an x-intercept. If you're looking for when a power line is in between 2 poles or when it's touching something, you're looking for those x-intercepts. And so x-intercepts are a big important piece as well. Right now, the only way we can find them is by using a graph and looking where they touch on a graph. We're going to learn other methods this week as well. We're going to learn how to do it through factoring, and we're going to learn how to do it through using the calculators. They can tell you automatically themselves too. And the last important feature of a quadratic is the maximum or minimum value. So because they have a swoop to them, they're either always going to have a highest point or always going to have a lowest point. That highest and lowest point on your quadratic is always going to be your vertex. It's always going to be that point at the very end of the quadratic. If your quadratic is going up, you will always have a minimum. It's always going to be the bottom of your quadratic. So if you have a positive quadratic, it's always going up. or it's going to be a minimum. If you have a negative quadratic, it's always going to be a maximum because it's at the highest point. One way to remember when your quadratic is going up or when your quadratic is going down, if A is a positive number, it's a happy quadratic because it's a smiley face. If A is a negative number, it's sad and it's a frown face. That's one way you can remember the cheesy method. But once again, your maximum is always going to be either the highest point or the lowest point, maximum, minimum. It's always that vertex. What is the highest point of that quadratic, the lowest point of the quadratic? And sometimes if it's off-center, like we have on this case or like we have on that second case, your maximum and minimum might not be just an easy point that you can determine very quickly. You might have to look, okay, this is at 1, -3. And sometimes you might have to use that graph. That's one way to find it. There is another way of finding your maximum and minimum. If you take negative b divided by 2a, so if you look at these numbers, take the b and divide it by 2 times a, so negative b divided by 2 times a, that will always equal the x coordinate of your vertex. And if you take that number and plug it back into your quadratic, if you figure out what is x or f of whatever that number is, and figure out what that answer is, that will always be the y coordinate of your quadratic. So it's pretty easy to do it from a graph, but sometimes if that number isn't an exact number, sometimes if it's like 3.2 as your x and then 47 as your y, it's kind of hard to see that on the graph. And so being able to do opposite of b over 2a, plugging that into your function and finding that answer is an easy way to find those 2 points without having to do a lot of extra work. So we'll look at some examples of how to do that as well. Questions so far of any of these 3 values, any of these 3 key features? Once again, these are the main 3 key features we'll be talking about. We'll spend a bit of time next week talking about x-intercepts and a bit of time this week talking about x-intercepts because those are important ones. But we still want to, we'll spend more today doing the maximum. All right. So looking at this graph, we want to find some key features. So do you see any of those 3 key features from this graph? Can you tell any of those points? So our y-intercept is, we're touching at 6. And so our y-intercept would be 0, 6 would be that coordinate. Yes?
For the x-intercept, would there be 2? It'd be 0, it'd be -1, 0. 2.
-1, 0, and 3, 0. So because it has that curve method to it, we have 3 possibilities for a number of x-intercepts. You could have either 1 x-intercept, 2 x-intercepts, or 0 x-intercepts. So possible if the quadratic is above that x-axis and going up, it might never touch that x-axis. And so you will have one of these 3 options for the number of x-intercepts, 1, 2, or 0. In this case, we have 2, because we cross down here at -1 and at 3. Are we okay with those points? Mm-hmm. What about the maximum or minimum points? Do we have a maximum or a minimum in this case? Is 8 the lowest value this quadratic hits? Ashton, you're shaking your head. What are you thinking?
What?
Do we have a maximum or a minimum on this quadratic? It's a maximum. So because we're going down, our highest point is going to be that vertex. And so the coordinate of that vertex, if we look, is 1, 8. And that would be your maximum of your quadratic. So you can find all of these 3 key features just looking at the graph. Assuming the quadratic has some nice points that it's touching and it's not ugly and not like going through halves or none of the points are on direct lines. Are we okay with that, where we pulled all these points from? Finding from a graph? Once again, if it's going down, if it's opening down, it's a maximum. If it's opening up, your vertex is at the bottom, so it's a minimum. So this time, we're going to try to find the same things, except we're going to do it without a graph. We're going to do it with just these values. We can't find the x-intercept just yet. We're going to learn how to do that tomorrow. But we're going to see if we can find the y-intercept in our maximum or minimum. So we learned that the y-intercept represented one of those numbers on there. Which number represented the y-intercept? Ashton?
It would be up there, 4.
Where'd you get the 4 from? There's 2 4s.
The 4 without the x.
So that last number was always your y-intercept. So in this case, our y-intercept would be 0, 4. So it's always that last number is going to be your y-intercept. Now, based off of this function, based off of that equation, do you think this is going to be a minimum or a maximum for your quadratic? Destiny, where are you getting minimum from? Just guessed? What changes whether it's going to be a minimum or a maximum? What changes about the quadratic? When can we tell if it's a minimum or a maximum? If it's opening up, is it a minimum or a maximum? If it's opening down, is it a minimum or a maximum? So this is the minimum, maximum. What changes whether it's opening up or down? What changes that? The number in front of the x squared. If it's positive, it's smiling, it's going to be going up. If it's negative, it's frowning, it's going to be going down. So do we have a positive or negative number in front of our x? Positive number. So because that's positive, we're going up. Are we going to have a minimum or a maximum? We're going to have a minimum. And then on that last slide, we said in order to determine this minimum, we're going to use, we have to first figure out what is negative b over 2a. We have to first figure out that number, and then we're going to plug that number back into the quadratic to get the y coordinate. So this will give us our x coordinate. Plugging it back in will give us our y. So what is my b from my quadratic? So it always goes A, B, C. So what's our b? We're just going to talk about the coefficient. Don't worry about throwing the x in there. Sorry, I should have specified that. So negative 4 because it's negative b, and then 2 times a, which is 2. So negative 4 divided by 2 times 2 is 4. What's negative 4 divided by 4? Negative 1. So that's the x coordinate of my minimum point. That's the x coordinate of my bottom. In order to get my y, I'm going to take that point, I'm going to plug it back into this function. So I need to figure out what is f of negative 1. So all we have to do is plug negative 1 in for each of those x's. So that's 2 times negative 1 squared plus 4 times negative 1 plus 4. So I just plugged negative 1 in for each of those exponents. We're evaluating a function like we've done earlier in the year. What's negative 1 squared? Negative 1 squared. Negative 1 times negative 1. It's going to be a positive 1. Negative times negative will give us a positive. So positive 1 times 2 is just 2. Negative 1 times 4, negative 4. And then plus 4. 2 plus negative 4 gives me negative 2. Plus 4 gives me positive 2. And so negative 1, 2 would be my minimum coordinate point. We're going to practice more with this tomorrow. We're going to practice being able to figure out what these values are from a graph and being able to figure what these values are from a graph, being able to figure out what they are from the function. And then we're going to learn how can we find these intercepts, that x coordinate, that y coordinate, or those x intercepts from these functions tomorrow. That's what we'll end it today.
Yeah.